For number one, we worked on part A, and then we were looking at part B, and we're trying to figure out, says that these hot bands correspond to these type of transitions. And ultimately the question is asking, does the matrix representation of negative E times the X operator squared help explain the hot band observations?
Say that last part of it.
This is, here's a question, the intensities of these hot band absorptions were very strong, much
Oh,
more
yeah,
than
yeah, yeah.
expected.
Yeah, okay, well, now hold on, so you did have a matrix form,
Yeah.
right, you have a matrix form of X, right?
Yeah.
Yeah.
Okay, now what is, what does this represent though? What is any, so I assume that you have noticed that the diagonal is 0,
Correct.
and you've got off diagonal entries. Okay. All right, fine and good. Well, what does this fundamentally represent?
The possible
The what?
no, the transitions, like the
Allow transitions?
allowed.
Okay, now hold on. It represents the allowed transitions. That's information, but it's not anything I can act on.
Okay.
Well, here's a picture of an allowed transition. S to a p orbital. That's a representation of an allowed transition. It's ultimately ink on a board, so it's kind of useless. So maybe you can give me a little bit better description. What does it mean to represent an allowed transition? Does it mean, so like the Laporte selection rule says that to preserve angular momentum of light, which is 1, you have to have hydrogen go from 1s to 2p, depending on polarization of light. Anyway, that represents something. Now, this is technically a vibrational transition. So again, what does it represent?
Would that represent the energy needed for the transition? Or the
No.
energy of the
Final
transition?
state.
No, it does not. That actually, what represents the energy of the transition is the energy of the final state minus the energy of the initial state. That corresponds to entries.
Okay.
Which entry you're talking about determines that. So this one, that one would be for the excited, I may be getting this wrong, excited vibrational state going to the ground state. So that'd be like stimulated emission. That's like fluorescence, that's infrared fluorescence. Some things do fluorescence in infrared. And then this one would be ground state to the first excited state. Okay, so now I would use QM to determine the energy. So that energy difference, which is the same, this is just the fluorescence emission wavelength, and this is the absorption wavelength, which technically are the same at this kind of lower level of quantum mechanics that we're doing right now. But anyway, so that determines the energy, that there is an entry, but the entry itself, the number here. You don't remember? I said it. I think I said it in class. No one remembers? You remember? Yeah?
What, I mean, can you frame the question again? I'm sorry.
Again, what did these numbers mean? I mean, you said it's a representation, and I can represent it as a picture. I can paint it on a billboard. What does it mean? Now, it's a number, so it seems like you can't just say it's a representation because it's a number. Okay, sure, how does it represent? Right? It's a number. That's gotta mean something. I mean, I could fill this matrix full of pictures, you can technically do that, it's weird, but I could do that. I could put this matrix and I could put a picture of the vibrational states that are transitioning, and that's a representation.
Is it something like an intensity?
The what?
Intensity of?
Yes, it's the intensity of the absorption. Right, so you probably just don't remember that from class, but basically the Beer's law coefficient, the Beer's law epsilon is proportional to the strength of the dipole transition, which is this. Oh, sorry, no, that's not quite right, that's not quite right. It's final state. Right, this is where these are, this is where this is a little different. For spectroscopy, you have different states in your Braun and Ket. The reason is that average position or average dipole moment could be done this way for the ground state or first excited state. So excited state. That's great. So what? A transition, a change in dipole moment is what makes this work. And that technically, you take your expectation value and you make a slight change to it that you had your initial state and your final state here. So that it's the same thing as expectation value with the slight twist that they're not the same state on the left and right. So this represents the change in dipole from initial state to final state. The bigger the number, the bigger the Beer's law coefficient. The bigger the Beer's law coefficient, the more absorptive it is. Right? So, now also notice that I told you that these entries are interpreted as the change in dipole moment, that there's some constants out here, right? Right, so you can generate this by, you can take these guys and represent it in the basis set of vibrational wave functions, which is what I've done here. These constants are out here. And so, yeah, so where the entries are can give you the energies, and the magnitude of the numbers can then be related to the Beer's law coefficient. Well, you probably, now actually I think the numbers come out to be negative for a weird reason. So technically it would be this, right? The absolute value of things are, remember that the dipole operator is actually for X-polarized light. Vibrations are only in one dimension, so we'll call it X, right? I mean, we live in 3 dimensions, atoms live in 3 dimensions, but if we're talking about like HCl, you can just say it's just one-dimensional because there's only one vector between the H and the Cl, so let's just call it X. So there's technically a minus E here, so technically you pick up technically these come out to be negative. And it's weird to have a negative intensity, but let me just remind you that ultimately everything gets squared. Everything's an absolute value squared. Anyway, that's a minor, no one cares about that, it's a minor detail. It's the magnitude of those values, right, is related to the Beer's law coefficient. That's right, that's it, that's kind of the answer. Right? If you built your matrix correctly, that's the answer. Right?
Yeah, I thought maybe we needed to square the matrix or something.
Well, again, because there's a weird minus sign, because electrons are negative, these entries, I think, end up, yeah, they're negative, right? But again, then you'd have a negative epsilon. Not quite, it's actually related to the square. Again, these are not important. I mean, there's a clear difference as you go down the matrix. As you go down the matrix, you're looking at different transitions. So what separates the ground state to first excited state versus the first excited, and I'm asking about the first excited to the second excited. So that's what you're observing. So what it comes down to is, if I can look at the absorption spectrum from CO, and it's attached to a metal, whatever, it's just CO, and you were to see it in its ground state, but if I was to somehow magically energize all of these so that they're in their first excited state, they would absorb to their second excited state, right? So that's this transition right here. So now, due to inharmonicity, you would have this occur at a slightly lower, lower energy. So here's the magic. So if I could somehow energize these into their first excited state, and then an absorption spectrum, an FTIR, would report the first excited to second excited transition, then what I'm saying is that the intensity would be greater for the same number of COs for the ground to first. That's what I'm saying. So again, ground state to first excited state has a Beer's law coefficient of say 10,000. That would be a big number. And again, if I can magically put the same number of COs under the same experimental conditions all in the first excited state, absorption, it's not fluorescent, so it would go to the second excited state. And I'm telling you, the registered absorption would be not 10,000, but 17,000. Right? Okay, now does the matrix explain that? Doesn't it?
I guess what we were confused about when we squared the matrix, there were,
Well, I don't know you need to square the matrix.
Yeah.
Again, let's not worry about the fact that they're negative. No, you just, okay, why are you squaring the matrix?
well, our idea was, I thought that was maybe like a way to like understand, sort of like what's happening with these hot band things.
No. Now, are you squaring it because I mentioned the intensity is the square, the absolute square?
Because that.
Yeah, well, I don't know why you're doing that.
That's the matrix representation of this explain this observation.
Okay, so I'm still saying this, right? Okay, so you're squaring the matrix. Does that correspond to this?
No.
No, what you're doing, you're calculating this. You're calculating that. You're calculating the dipole operator times the dipole operator. I don't know what that is. I don't know what that corresponds to. It has nothing to do with UV. It has nothing to do with absorption spectroscopy. But you don't square it.
This expectation.
It's just, well, weird expectation, really, with different states. Now, what you wanted, now what did you do, how do you do this? You don't square the matrix. You take the entries and square them. There you go. Right. Yeah, you way overdid it. This is the easy problem, right? I know the programming is going to take most of your time. These questions are just to kind of, you should have some questions based on this stuff. This was kind of an interesting problem that happens, and especially if any of you, there's some GLUSAC people, and they're actually going to see this. I saw it all the time, and so will they. And this is why you can see hot bands so well. As long as there's inharmonicity that causes, see, remember a true parabolic potential surface, the energy spacings are identical. So again, most things are in the vibrational ground state. So 99.999% of what you're observing is ground state to first excited state. But when you do pump probe spectroscopy, you actually are gonna get an appreciable population actually in the first excited state, and then your absorption is measured from from first state to second state, like I drew here. Now, technically, that would be at the same spot in a purely harmonic potential, but in an anharmonic potential, there's actually, the hot band is actually shifted to lower energy. So you can actually observe it, and that's what you see in my figure there. You're seeing the hot band absorbing at a slightly lower energy, so it's observable, and it was very strong. Normally I don't see them, but I did in this case. It was really just glaring that I could see this hot band. And this is why I can see it so well. So there you go. This is the kind of things that, help answer your observations in lab, which is, part of this is to change your mode of thinking. We also want you to be math savvy. I'm hoping these programs will be helpful in your future, but there's also, some kind of hope that some of the things you learn will occasionally, you may see them in your research. Anyway, all right. Well, now what? Because that's really all there is. This is actually really simple.
Number 2 was fine. We didn't make any progress with number 3. I'm not sure if you did. If you have a question about number 3.
I don't even remember what these are. I wrote these a while ago.
3 is the quantum dot.
Well, you just have to write a finite difference code, right?
Yeah.
Well, it's not too bad. Of all the programs, it's probably one of the longer programs you've written, but if you're going to be in the physical division, one of the things that distinguishes us is our ability to take data and analyze it to its fullest. Makes you the smart ones in the chemistry department, right? Because math is hard and people don't want to do it. Now, I personally see it as a differential skill because I'm kind of a synthetic chemist. But if people want to call you smart for doing math, let them. All right, but learn to do it though. All right. Well, that's it. I gotta go to the store.
Is there a difference in what is the difference in potential energy between the shell and the core?
Well, now remind me the nature of the problem. I think I asked you, all right, so I think you're doing this,
Yeah.
right? Okay, well, and you're doing the electron, right?
Yes.
Right, there's electrons in holes. Okay, and then what I did was, I sent you some data, which was the first data I ran into on Google. Okay, so now remember, there's this thing called the effective mass approximation, which works like this in a diagram of energy. And let me do radius 0 to 10 nanometers. What you would have are so in a material, you would have your valence band, and then you have a conduction band. And so this is for a semiconductor. And what happens is upon absorption of light, an electron goes from the valence to the conduction. Okay, a weird thing about these, as much as we think like, well, semiconductors, conduction, electronics, we only care about electrons. There's some anomalies that cause people to realize that the absence of an electron in the valence is just as important as the electron. So the electron, of course, is a real particle. It has a mass. It's measurable. But the absence of that same electron, the electron was in the valence band, and it's not anymore. And there's a consequence for the valence missing an electron now. So the properties that you observe are half of this electron, which is really in the conduction band. You can measure it but you're gonna see other things. And those other things are a manifestation of the lack of an electron in the valence band. Now, let me give you an example. Now, again, I don't think you have any problem imagining an electron, right? I mean, because you know about electrons. Okay, now, the absence of an electron is also just as consequential. And so it's sometimes called its own particle a hole. So it's like it's like a positron. So it's an electron with a positive charge. Now the reason that we model like two electrons, one of them is positive, is imagine this. Imagine that you wire this, right? Now think about this. So you want current to flow. You want current to flow through this thing. Okay, now if you're going to wire this and you're going to have a negative potential and a positive potential, and so this, and now again, what you're going to measure, you're going to shine light, and you're going to see this electron go to the left, and you're going to measure that as a current, right? So no problem. I mean, this is like middle school stuff. But I'm saying you're going to actually observe two electrons, not one. Isn't that nuts? What's going to happen is an electron from the wire can jump here. You see? Real electrons can flow this way, but electrons can flow the other way into here. So what the real electron goes this way, but electrons, by virtue of the fact that this is still connected to a metal, can go that way because this hole allows them to jump from the wire into the material. And now you've registered, see, you know, this electron has come this way, and you've registered it, but another electron has gone the other way to fill that hole. So you're actually seeing two electrons migrating in the wire. So just my point being is that semiconductor electronic structure unfortunately ends up being a little complicated. So when we modeled these, we modeled the electrons, and then we model a quasi-particle in the valence called a hole. Now, so I didn't want to blow your head off. I think I told you to do the electron, right? Now, those band gap diagrams, I think you see electron and hole. So, can you show me what I kind of remember. So you're seeing electron and hole, and I know I didn't really explain that, but then again, you're in grad school and you're gonna have to figure these things out, right? So anyway, so I just explained it, but I told you to model the electron. Okay, now to read this sucker off, so that's why you see something like this, and it's labeled as electron, right? And then you have another thing like this, and this is the hole. Okay, and let's say this is CDSC. Kind of actually more accurately like this. This is CDS. So what you're seeing here is like here's the core, and here's the shell, and these are the potentials. So when you shine light on it, you're going to get a hole here and then an electron here. Okay, now the electron sees something of a barrier to go in Cad sulfide, but not a big one. The hole, for various reasons, it's since it's an anti-electron, this dip is actually a barrier. So that's another thing you have to, that again, if any of you do semiconductors, and I think actually all of you are going to do semiconductors, holes, since they're really anti-electrons, a downward drop is actually a barrier, because everything kind of does the, remember they're not real, right? It's the absence of an electron. So it like, some people say holes are electrons that move backward in time, and that would be completely accurate. But anyway, okay, but your job is to model the electron. Okay, now based on this potential surface, let's call that zero potential. Let's say that's like 0.24 eV. Is that right? So again, notice I gave you a couple. It looks like I gave you Cad telluride, Cad selenide, Cad telluride, Cad selenide. Oh, look at that last one, Cad selenide, CAD telluride, CAD sulfide. See that last one? Okay, can you figure out the barrier for CAD selenide to CAD sulfide in the electron from that last diagram from D?
This is one.
Actually, no, sorry, you can do it, well, actually you can do it in B too, right? So what's the barrier?
0.21.
There you go, 0.21. Okay, so to however many, to the core radius, you could have, sorry, it's like the potential, you could have it be, zero after the core radius, you could have it jump up to the shell thickness. And after that, you could jack it up to, I don't know if I said, but in the exterior world, the electron does not want to go into the exterior world. This semiconductor, if you were to literally shoot electrons at it, they would go into it and stay there because they don't want to be out in the free. You can just shoot electrons into the vacuum. That's how TEMs work, that's how old televisions work. But if they can go into something like a material, they'll soak it up like a sponge. So, so for the electron, so the exterior world acts like a really big barrier for the electron. So that's why I'm saying there's no barrier for it to be in the core, a rather modest barrier. That's a very small number for the electron to be in the shell, and then to leave the quantum dot completely, there should be a very high barrier. I don't know if I suggested a number. I typically use 3 eV, sometimes I use 10. Yeah, I typically use 3 eV. So notice the scale that I have. 0 to 0.21 to 3 is rather large. And that would go out to the length of your simulation. So that's your potential trap. There you go. And I could ask you to do holes, but again, I didn't want to blow your head off, but I did want you to know about holes. Now, what you would find is that in your particle in the sphere, so let's do the wave function. So a particle in a sphere, and we remember we did this a while ago. It has to go to the wave function has to go to the core radius. Remember, it's like sine r over r. That's basically that's a particle in a sphere wave function, right? But now what you're going to find for a core shell is going to be something more like this. Right, it's going to leak out, it's going to leak into the shell. Well, it's supposed to lose a little amplitude, it has to lose some amplitude, it still has to be normalized, right? So, remember the energy, you should be able to calculate the energy of I forgot what it is, 0 squared, h bar squared, something like that, or 2me, anyway. Right, remember, we did this a while ago. You had to calculate this, the energy of a particle in the sphere. Anyway, it's something like that. And your calculation could do that. What you could do is just at the core radius, jack up the energy to 3 eV at the core radius and see what energy you calculate. And then it should match to this. And remember, everything is in atomic units, so the energy would be in Hartrees. So then you add the shell, and you get a wave function that spreads out a bit more, and you're going to get a lower energy. So that's why when you're doing, if you do absorption spectra on a quantum dot, and we'll work in nanometers, which is unfortunately inversely related to energy, what you see is, here's what the core, and then what you can do is add a CAD sulfide shell, and what it does is, it redshifts it. It redshifts it because right here. There you go. So, yeah, so these are the fundamental physics that you're trying to repeat with your quantum mechanics. And again, there is so, we've done enough at the beginning, we had flat potential surfaces and we made wave functions smooth and continuous. You can actually do that here. That's one route to do this problem, is to use the approach we had at the beginning of class when we were taking flat potential surfaces and making things smooth and continuous. And that seems like a lifetime ago, but you can actually do that with particles in a sphere. Or, again, you can see why I do what I do, or I write a code which I can actually do way the hell faster and even make this potential surface way more complicated and get answers that way. At the end of the day, I kind of prefer what's easiest if the results are correct. I can still draw my wave functions, that's what we want anyway. It's a little cheap, I don't think it's a little cheap, but I mean, it works. Alright? So, make sure your wave functions are correct. Now, one thing is, note that these have different masses. So in this theory, this theory about electrons and holes is called the effective mass approximation. When you do that, when you're going to model the absence of an electron as a whole, a consequence of the derivation to make sure all of this okay means that the masses are no longer what they should be. And so the mass of an electron is 9.10 something to the minus 31 kilograms or something. Anyway, when you analyze like the conductivity using this theory, because we can measure the conductivity of semiconductors, when you measure the conductivity and fit it to this theory with electrons and holes, the problem is that the mass has to become an empirical parameter. It has to be measured. So it's a little funky. The masses are almost always less than the actual masses. Now, of course, the electron's mass is still the electron's mass, but in this theoretical framework, it becomes less. And again, it's just because we're having to do electronic structure theory with approximations. And the consequence of an approximation means that something gets messed up. What gets messed up is the mass. The whole will also, again, there is no hole. It doesn't exist. But to pretend that there's a positron in the material as there is an electron will answer 95% of all of your questions about semiconductor physics. So people really like this model. But it is just that. It's just a model. So the hole that's not even real also has a funny mass. They're usually less than an actual electron, typically. In some weird materials, sometimes they behave as if they're heavier, but that's rare. Anyway, so that's where that comes from. So when it comes to setting the masses, remember you've got two parts of the program. One that sets the potentials. You can do that before you do all those operators, before you make the matrix. And then in the matrix itself, you're going to want to set the masses. The Hamiltonian matrix, because the Hamiltonian matrix has minus h bar squared over 2me, where me is the effective mass. Times the Hamiltonian operator. Of course, this is actually 1, so this is actually minus 1/2. So it ends up being that and atomic units. And then of course you've got your matrix. And the matrix of course is minus 1 over 2r plus v. So this is in the 1, 1. Then what is this one? It's 1 over r. Then what do you got over here? Minus 1 over r. R squared, right? something like that, right, for, right, you see them building a matrix. Anyway, I'm not quite getting it just right, but right, you build a matrix that is del squared, right? All this is del squared in the finite difference paradigm, and hopefully you know what I'm talking about because you had a class on it. And I'm kind of remembering the operators. And remember that this row represents an R of like point 0.1, this is 0.2, this is 0.3, so that's what goes into R. And all of this is multiplied by 1 over 2me, but remember, it's a function of radius. So at some point, when you get to the shell and to the ligands, your Me changes. Your Me the constant that you multiply all the entries by is going to change. Right, you see that? So again, this is the core. This is the core row. So it has the core mass. And you're going to have that for about like 100 of these rows. This constant that multiplies the entire entry. And then when you get to an R that corresponds to the shell, those rows have a different constant. And then when you get to your 500th row, 500 to the thousandth row, then your Me, you probably want to use the number 1, which then is like a real electron. Outside of the quantum dot, you're not in the effective mass approximation. So the mass, you can say the mass should be 1. It's a real electron at that point. So that's another thing you've got to look out for. And did I mention that? I mean, I did write the thing. Yeah, I mentioned effective mass approximation. I mentioned holes. I didn't want to go off on that too much, but
Oh, no.
no. Did I mention the masses? Yeah, I did mention the masses, right? So anyway, that's how you deal with the masses. That so potential in my example code, I said I calculated the potential ahead of time. It's nice because you can check it out, make sure you did it right. And again, it should look like this. And then when you set up the matrix, the finite difference matrix, it's supposed to be multiplied by these constants, but it's actually going to depend on what row. So you're going to have to do a little extra coding to get that to work right. Yeah. And remember, this is the easier of the two. The other one's way harder than this. When you're done with this, this is going to be, you know, this is maybe 20 lines of code. It's not terrible. The other one's going to be about a whole page. Right? That's about half a page. The other one's going to be about a full page. And the thing that's nightmarish is that everything has to be perfect. That's one thing exciting me about programs. You got a factor of 2 in the wrong spot, it's wrong. Everything will be wrong. The cool thing is generally nothing works. When you do these quantum mechanical programs, I mean, you've seen this before already. You're doing quantum mechanics on a program, it's either fully right or it's not going to work. So you'll know it. And this is definitely true with this stuff. It'll just go haywire if you don't have it perfectly correct. It does need to be perfectly correct. Remember, when you get out of here, who gets paid the most? Physical chemists. You're paid higher than synthetic chemists. You actually can make a lot more money than synthetic chemists. Why? Because of crap like this. Synthetic chemists don't have to, I mean, look, to their credit, right? They don't have to live in a world where every reaction is 100%. You do. Your code has to be perfect. Just like a synthetic chemist would have to have 100% reaction yield on every reaction. That's physically not possible. Let's say it was. Would you hold them to that standard? That would suck. That would be awful. Anyway, you get my point. So being good at math, having, you know, this absolutism in terms of is it right or wrong that you live in is worth a lot. And you will be compensated for it, so cool. Yeah. Well, what else? Because I gotta go try, I need to get yogurt.
I think that's all we've got for now.
All right, well, tell you what, send me your code. When you get stuck, send me your code, because I usually can, from my perspective, this is, I can figure out your code real quick. I mean, everyone's code is, it's one thing. If you're working together, just be careful, because code is a reflection of personality. You think there's only one way to write the code? Oh, that's not true at all. If we're working together, I'm gonna know it.
Question on the split operator?
Yeah. Split operator.
That's the harder of the two, I'm telling you.
Yeah.
But that's the more powerful, because you can do 3 dimensions. You can do 3 dimensions with a finite difference. I'm not actually sure how to code that. I've never figured it out. It's actually kind of proprietary. That's how that program COMSOL works. Wait, no one have any other questions? Are we?
Maybe just to get us maybe started on question 4, because I'm a little confused even how to start it.
Start what?
The question, like, from what I'm seeing, that you gave us 3 choices of a potential surface.
Wait, no, this is, sorry, which question is this again? Split operator. Oh, yeah, so just, okay, how do you do, that one is not done.
You said, you have to be careful where you start the wave function on the surface.
Yeah, all right, now on this one, all this weirdness with the finite difference method. Remember, finite difference method is really one-dimensional, but if theta and phi don't matter, you can actually make your one dimension radial. So you can kind of trick it into doing 3 dimensions, as long as phi and theta don't matter, which is true of ground states. Now, finite difference, split operator is kind of cooler because it can handle 3 dimensions. So what you're going to do, well, not in this case, I just want to point out one of the things that's cool about it is, if you want to, like in that example I sent of a hydrogen atom, what that was done is I created a 3-dimensional grid. So the wave function is literally amplitudes inside of that grid. Okay, so whatever, I'm just pointing out that it's grid-based. It's not, in its real space, it's not radial. Now, I actually asked you to do a 1-dimensional problem. I should have done 3 dimensions. I asked you to do 1 dimension, right? Okay, so that means that in MATLAB, of course, the array, that is your potential surface, your surface, goes from 1, 2, 3, 4, 5, 6. So what you want to do is, have some grid spacing, dx, which will be, again, we want to do things in Bohrs. You want to use things in atomic units, so let's make it like 0.1. There's not too many chemical problems where grid spacing, anything less than 0.1 Bohrs would ever be necessary. So now you've got, okay, then, so you can say you go up to, I'm just being rhetorical, then subtract 0.5. And again, now remember MATLAB's array index is still 1, 2, 3, 4, 5. Okay, so now you've got your track with 0 in the middle. All right, now with that, you can define the potential however you want. Just say potential, make it 100. So that in Hartrees, that's a big number. Um, you can do something like this. Now, again, I would recommend a bigger. Alright, so look what I've done here. I've just made a potential surface that looks like that. I'll go 100. Actually, you might want to go to 101, right? Because the first one is 1, so you want the last one to be 100. Anyway, it's a minor detail. Anyway, well, there you go. I just created a potential surface. And then, then you have to make the split operator. Now, I'm forgetting exactly what it is, but it's something like this, right? And again, look at my example. So there, now you've got your operator. And then, now your kinetic operator, your kinetic energy operator is a little bit more difficult to understand. Anyway, you have example code on that, and you should be able to reverse engineer my example code to figure out what the kinetic energy operator does. And then when you're actually time evolving, you want a pretty big one. What you do is you so you'd also would create when you're doing all this. Don't forget to create a wave function, an initial wave function. I don't know, something like that. And so that's what I meant by be careful with your initial wave function. Make sure you define your potential, make sure you put your wave function into the trap, create the operators, and when you actually do the split operator, or it's, I forgot, it's K. Then you reverse Fourier transform. Then you operate with the potential energy operator. Then you inverse and operate on the, anyway, this is approximately how it goes. So your wave function is defined here, and it's in real space. So the first thing you do is you Fourier transform it to inverse space. The kinetic energy operates on it. Then you convert it back to real space. In real space, the potential energy operator acts on it. And then you reconvert it back to inverse space. Then you do the kinetic energy operator again. And then it loops. Actually, This should be up here. You have to be real careful on this one. Oh, there's a delta T in here. There's a delta T, anyway. So again, before the loop, inverse it to momentum space, operate it on it with the momentum operator, transform it back to real space. In real space, it gets operated on by the potential operator, which is a real space operator. It's fine and good, transform it back to momentum space. Momentum space, it gets acted on by the momentum operator again, and it loops back to be operated on the momentum operator again, which is correct. Remember that the split operator does it this way. It's it's like this. So for your transform it, do this. For your transform it back to real space, do this. For your transform it back to momentum space, do that. And then you actually go back here. So that's why you see this loop. You may notice it's going to go K, V, K, back to K. So it's doing K twice. But that's actually correct. Here, 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 over and over again. So you actually do K twice. So that's just a little, you have to be just kind of careful about that in the algorithm. And again, my example code, I believe, does that correctly. So this is the harder of the two, but it's way more powerful. And again, the thing that's awesome about this is to do 3 dimensions. Take every one of these deals, like here. So it's all about the potential and momentum. Take this. This is for X. And then multiply the same thing for Y. So you would have the potential you have the potential defined in the Y direction. Times. And then another one for Z. So it's really easy to make these 3-dimensional. And so as I've done there, I just added a Y direction just simply by multiplying the momentum operator, the potential energy operator just by another term, and then I would multiply by another term to create, now I'm simulating an object in 3 dimensions, which the split operator, the finite difference can do, but I'm not even sure how. It's very specialized. The split operator is very good about doing 3 dimensions. And again, it's incredibly trivial. You multiply exp times exp times exp. Potential x, potential y, potential z, which usually are the same number anyway, since usually things are symmetric. So last year I had people do 3 dimensions, but I decided to go easier on the end. Just had to do 1 dimension.
It's just setting up those boundary conditions that.
It's just set a potential trap, and then look, it's not hard to, multiply by I. What would that do? That would make it look like that. I don't know. Just whatever. The other cool thing is that if you plot it at this step, if you plot it here, while it's looping over time, you can watch the thing jiggle around. Now, I think I sent you code to do that, right? Watch it jiggle around. which is evolving times. And then mess with the potential service. It actually is kind of legit fun to do that. Yeah? So anyway, just doing that, it's very easy to change these potential surfaces. The thing that you could screw up though is that if you make it fly off, remember, 0.1 is a big number for energetically. If you set this to like 10 million, the algorithm will go crazy. You can't handle that. If you're gonna simulate a 1 nanometer object with a grid spacing of 1 nanometer, you're clearly screwing up. You're gonna want, at least 30 or 40, if you're gonna have a wave function, you're gonna want at least 30 or 40, if not 100 or maybe 1,000 points to accurately describe it. You can't simulate something like this with a discretization of space like this, right? Because then it looks like what would that look like? Anyway, you get my point. It's ridiculous. You have to, if you're going to simulate the curvature of a wave function, you need to have the proper grid spacing to do it. And again, there's no there actually are formulas to tell you what the optimal is, but reality is it's just best that you play around with it and figure it out until you're comfortable that the results are meaningful, that you're not calculating just junk, and that's why they pay you the big bucks. If you ever look more deeply into this, people have figured out ways of determining the error. Remember that the split operator method is an approximation. The whole thing is an approximation because potential energy and kinetic energy don't commute. Commutator of X and P is IH bar. So that causes tremendous problems, and that's where the split operator gets derived, and blah, blah, blah. So the whole thing is an approximation. There are ways to actually calculate the errors of your approximation. So if you look at some of the original papers that tell you how to do that, I'm telling you, if you screw up, you'll know. The simulation will go crazy. It will be immediately obvious when you look at what it did. Yeah? Okay?
Thank you, I appreciate it.
Remember, just send me your code.
Okay.
Go stay wire, let me look at it. I can figure it out real quick.
Okay.